Yep.
Hi there. That's Joe, and I'm Nico. We both work for the security response team at Microsoft. And we are here today to talk about Hyper-V, its architecture, and some bugs we've seen. So you guys, you might be wondering why us, Microsoft, is talking about bugs in our own product. Well, there are many reasons for that, but short, we just want the bugs. We want your bugs. And just so you know, we've got that amazing bug bounty for Hyper-V, paying up to $200,000 for just a kernel bug, triggerable from the guest. So just to be clear, we don't need an exploit. We'll just take a POC along with some quick description of this issue. That's enough for us. If you manage to get an exploit, it will be happy to get you 50,000 more. But we just need the bug. So why such this amount of money? Why is this so high? Well, because it's hard. And we think that we are really lucky to be here today giving this presentation because you guys, you have the skills. Some of you have been at Pontoon. You have found like amazing issues. You have found crazy exploits. And you guys, you have the skills to find these bugs. And that's why we are here today. We want to help you secure these amazing bounties. So Joe, in a moment, is going to talk about the architecture. And I come back later, and we'll talk about some of the bugs we've seen so that you can actually find other bugs and get some bounties.
Yeah, thanks, Nico. So the first thing we want to do, as Nico mentioned, is just show you guys a little bit how Hyper-V works, really from the perspective of a security researcher that wants to go and find these guest-to-host bugs. So I'm not going to bore you with architecture that doesn't matter. I just want to show you the architecture that will matter for you. So when we look at Hyper-V from a very high level, you can see that at the top here, we have the hypervisor. And the hypervisor is ultimately responsible for providing a number of services to the various partitions that run on the system. The hypervisor is responsible for managing the extended page tables. This is what allows the hypervisor to enforce that none of these partitions can see each other's physical memory, so their data is safe from each other. And the hypervisor also has the ability to intercept attempts by various partitions to execute certain privileged instructions. So if one of these partitions tries to do an I/O port read or write to talk to hardware, the hypervisor can intercept that and say, nope, you can't do that, I'm going to emulate it instead. So that's really the hypervisor's job here, is to enforce that isolation. The hypervisor is also responsible for a number of other things, such as delivering interrupts to the guests and managing some other virtualization-specific configuration.
Do you think, Joe, do you think it's worth spending time to look at the hypercalls, for example? Because it would be like the most obvious way for me.
So a lot of people get really excited about looking at the hypervisor and trying to find bugs in the hypervisor itself. But in my opinion, the hypervisor is not the best place to try to find bugs for a guest-to-host attack. The hypervisor really has very limited attack surface from all of the guest partitions. And so, yeah, I don't really think it's the best place to start. I've personally only found one bug in the hypervisor in about 3 years. Yeah. So not too great. So let's move on to the root partition. So one of the things that I just told you guys was that the hypervisor uses the extended page tables to ensure that all of the partitions running on the system don't have access to each other's physical memory. And that's actually not quite true. There's one thing to note there. We have this special partition called the root partition. And that's where the host operating system runs. The host operating system is responsible for managing all of the other partitions, which is where all the other virtual machines run. And so the root partition actually has access to the physical memory of all of the other partitions running on the system. And it needs that because it needs to do emulation sometimes, so to emulate a device that needs access to physical memory and CPU state. But none of the other partitions have access to each other's physical memory. The root partition also has access to all of the hardware on the system. So it has access to your network card, your graphics card, etc. And the root partition is ultimately responsible for providing a number of services to all of the other partitions on the system. And we'll talk a little bit more about that later.
So you think it's much more interesting to look at the components?
Yeah, I think that if you want to try to find guest to host escape bugs in Hyper-V, you really want to look at the code that's running in the root partition. This is where most of the attackable components live. And last but not least, we have all of the guest partitions. And the guest partitions are where all of the virtual machines run. So there's one VM per guest partition. They don't have access to any of the hardware on the system. They don't have access to the physical memory of any other partition on the system. They have access to a very limited set of hypercalls that they can use to talk to the hypervisor. And they have no way that they can directly communicate with any other partition on the system besides the root partition. So in Hyper-V, there's no real guest-to-guest attack surface. All of the attack surface is guest to hypervisor or guest to root partition. And one thing that I didn't call out earlier and that I meant to was that some of you guys might be familiar with some other virtualization stacks, like KVM, for example. And in a number of other virtualization stacks, the hypervisor itself is actually a driver that runs inside of kernel mode in the host operating system. And in Hyper-V, that is not the case. In Hyper-V, the hypervisor is a standalone binary, and it runs in its own physical and virtual address space. So the root partition, the host operating system, and all the other partitions, they have no ability to tamper with the memory of the hypervisor, for example. That's all isolated away from them. So when we're talking about virtualization, we end up talking about physical memory quite a bit. And in Hyper-V, we have a couple of different ways that we refer to physical memory. System physical addresses are how we describe the real physical address of something, so the actual hardware address. And guest physical address is how we describe the physical address that a guest sees. And the hypervisor maps guest physical addresses to system physical addresses using the extended page tables. In Hyper-V, we also have something that we call a gpaddle or GPADL. Some of you guys might be familiar with the Windows kernel programming. And in the Windows kernel, we have an MDL. And an MDL is just a list of physical addresses that describes some memory. And that's really all that a gpaddle is as well, except it is a list of guest physical addresses. So the guest can send the root partition a gpaddle, and it's just a list of guest physical addresses that describes some region of memory. In Hyper-V, in the root operating system, we have a couple different kinds of components that are typically attackable from a guest. The first one is a VDEV, or virtual device. And this is either an emulated device or a paravirtualized device that is hosted in user mode on the root partition. Then we have VSPs, or virtualization service providers. A VSP is a paravirtualized device that is hosted inside of the kernel of the root partition. And VSPs always have a VDEV that's associated with them. And then we have integration components. And from an attacker's point of view, there's really no difference between an integration component and a VDEV. It's just code that runs in user mode on the host operating system that is attackable by the guests. So what are the various partitions that Hyper-V needs to provide to guests? Well, there's a number of them, and they're not always used. Some of these are only used in specific configurations, like if you're using containers, or if you're using a Generation 1 VM versus a Generation 2 VM, or if you've enabled specific options, like if you've enabled live migration, for example. But from a high level, we have storage, video, networking. For Generation 1 VMs, we need to emulate a lot more hardware. So we have things like an emulated motherboard, an emulated PCI bus, etc. Just various hardware that operating system that doesn't realize it's being run as a virtual machine might try to talk to. We have paravirtualized devices. These are things that need to run super fast. So networking, storage, video, and we also have the paravirtualized PCI bus. And I'll talk a little bit more about that in a second. That one doesn't necessarily need to run super fast. And then we have sort of a grab bag of other things. So We have these integration components that provide things like a heartbeat service to see if your VM has actually just hung, and time synchronization so that the VM can use the same time that the host is using. Things like that. Now, Generation 2 VMs, they require a lot less emulated devices than Generation 1 VMs. So if you want to go after a lot of the emulators, you need to configure your virtual machine to be a Gen 1 VM. Now, Hyper-V really is designed with the principle of least privilege in mind. Whenever we add new code to Hyper-V, we always aim to give it as little privilege as required. So we don't add most of our code to the hypervisor itself, because it doesn't need to be there. And we also don't really put that much code in the kernel of the host operating system, because it usually doesn't need to be there. Most of the new code can actually just go inside of user mode on the host operating system. So if we actually look at Hyper-V from the perspective of where does all of this code live, which is really useful for me when I'm looking at what I want to attack, you can see that in the kernel, we have a variety of components. We have our paravirtualized storage, networking. We have paravirtualized PCI that runs in the kernel. And paravirtualized PCI exists to allow scenarios like dedicated GPU, where you have a GPU that's connected to your host, but you want to just give the entire GPU to a guest. And so you can use vPCI to just go and place that GPU in the guest, and the guest can directly interact with it. And it also allows scenarios like SRIOV, single root IO virtualization, where you might have virtualization-aware hardware that you want to share directly with multiple guests. We have WinHVR in the kernel. That's basically the kernel 32 of the hypervisor world. It just contains wrappers around hypercalls. We have the VM bus, which we'll talk more about later. It's a communication channel. And then we have the VID, or virtualization infrastructure driver. And the VID really is the glue that binds a lot of different pieces of Hyper-V together. It's the main component that interacts with the hypervisor itself. So when components on the host need to do things like register to receive notifications when a particular I/O port is hit so that they can emulate it, the VID is what they talk to, and the VID ultimately registers that request with the hypervisor itself. And then in user mode, we have a number of processes, but the one that really matters for you guys is the VM worker process, or VMWP. There is one VM worker process per partition, which is really nice for us, because it means if there's a bug like denial of service bug that a guest can trigger, if the code lives in VM worker process, it doesn't matter a whole lot to us, because the guest can just crash itself. It won't actually impact any of the other virtual machines that run on the system. And so this is where we put things like emulators. This is where we have all of our integration components. This is where we have components like the virtual SMB server, Plan 9 file server, and really a lot of other components. They all live in the VM worker process.
Yeah, a lot of the source code is already available online in the Linux source tree, so just check it out. Joe, do you have some insights of how these components talk to each other?
Yeah. So this is really one of the most important things for me when I'm looking at how do I attack some component is, how do I talk to any of these components, right? You need to know how to actually hit these things. So the hypervisor has a number of ways that you can directly or indirectly communicate with it. The most direct way that you can communicate with it are hypercalls, which are really just the system call of the hypervisor world. There's a number of hypercalls. Not a lot of them are actually exposed to guest partitions. So as I mentioned previously, I don't think this is the best place for you to really start looking for bugs. And you actually don't need to know how the hypervisor works at all to find bugs in the other components. You could completely ignore it. There's a number of other ways that you can end up indirectly communicating with the hypervisor, but we don't have time to really go in depth into all of them. But you could follow up later if you're interested in any of these other ways. So for kernel mode components, there's a number of ways that you can communicate with them. All of the virtualization service providers end up using the VM bus, which is a high-speed communication channel that we're going to talk a little bit more in depth about in just a second, so just hang with me there. All the kernel components interact with the VM bus through an abstraction layer called KMCL. Another way that you can interact with kernel mode components is through extended hypercalls. And there's not a lot of these, but I figured I'd mention them just for completeness. Extended hypercalls are hypercalls that the hypervisor just forwards directly to the vid to handle, because the hypervisor can't handle them itself. We also have something called apertures, which I'm going to talk more about in a second because they're used more in user mode components than in kernel. And then there's intercept handling. So the hypervisor will forward what we call intercepts it receives, which are really just traps to the guest, to the host for processing. So examples are when you receive a I/O port read or write, the hypervisor will intercept that, and then it will pass it down to the vid to decide, hey, is there a component that needs to emulate this? And then the vid will handle forwarding that along. The same is true for things like extended page table faults. So if an extended page table fault happens, that might get forwarded onto the vid because it might mean that there is a MMIO emulation that needs to happen. And finally, we come to user mode. And there's a lot of ways to talk with user mode components because we have emulators that live in user mode. So we have I/O ports. You read or write to an I/O port. It traps to the hypervisor, down to kernel mode on the host, and then finally to one of these emulators that requested to receive notifications. MMIO is similar. So if you talk to specific physical address ranges, that will be forwarded along to some user mode component where it can emulate the MMIO read or write. We once again have the VM bus, which I'll talk about in a second. And we have apertures. And an aperture is just a concept that we use to describe effectively creating a shared section between a guest and the host. So what this means is that the host operating system creates a list of guest physical addresses that it wants to map inside of its virtual address space so it can read or write to them. And then we have read and write notifications, which are really similar to MMIO with one key difference. When you register for a read or write notification, you will be alerted anytime some guest physical address is read or written to. But you can't actually emulate. So you are just notified that this read or write is happening, but you can't say, oh, here, return this 8 bytes of data for the read. And this is used for things like live migrate, where you might want to mark if a page is dirty or not so that you know you need to retransfer it over the wire. So let's talk a little bit about the VM bus, because this is how a lot of kernel components in Hyper-V can be accessed, and also a number of user mode components. So VM bus is a communication channel that is built on shared memory. So the guest and the host agree that they will use certain guest physical addresses as a ring buffer. The guest and the host can both write data into this ring buffer and then signal the other side that data is ready. There are a couple ways that components interact with the VM bus. They never interact with it directly. Kernel components interact with it using KMCL, which is the kernel mode client library. And user mode components typically interact with it using either VM bus pipes or VM bus sockets. If you want to know more about how the VM bus works, once again, the Linux integration drivers, as Nico mentioned, contain a full implementation of the client side of the VM bus. So you can use that to understand exactly how this protocol works and exactly what the structures look like that are getting passed around. So that's really useful. All right, so KMCL is the abstraction layer that most of the kernel components use. It's used by VMswitch, the storage virtualization service provider, and vPCI. And it's really built around callbacks. And at the end of the slide deck in the appendix, I've actually gone and listed a bunch of the different callbacks that a lot of the communication channels use. So you guys can go and reference that if you want to actually look up these different interfaces. The gist of it is that whenever you receive a message over the VM bus, you receive a callback to some function pointer that you provided KMCL during initialization. The message that you receive is copied into pool memory on the host. So there is no risk of race conditions happening if you fetch data twice from the message, for example. That message is copied completely into safe memory by the time a VSP receives it. However, there is a concept called external data when you're interacting with the VM bus. External data just means that when the guest sent you a message, it attached a gpaddle to that message. So it sent you a message, and then it also sent you a list of guest physical addresses that contain additional data. Now, the guest can go and it can map that gpaddle just like an MDL. So it can map it right into its virtual address space and start interacting with that data. But one thing to keep an eye out for is that you need to be extremely careful if you do this, because that data is mapped in both the guest and the host at the same time. And so you are vulnerable to double fetch type issues if you aren't careful with what you're doing, because the guest can be changing that data out from under the host at any time. So as I noted, there's more function definitions at the end of the slide deck, but basically this is just a function call that you use to set the callback that you want, and you can see, let's see if I can use the laser pointer here. Yeah, I don't know how it works, but basically there's a message here that comes in. It has a buffer. It has a buffer length. The buffer contains the data that the guest sent you. The buffer length is the size of that data, and that's all in trusted memory. The next way that you can interact with VM bus is via pipes. So the guest can create a VM bus named pipe, and then it just interacts with it just like using normal named pipes on Windows. So you can just call read file, write file, or you can do I/O completion if you want asynchronous I/O on your VM bus pipe. And I've noted some functions here to go and look at if you want to find places where VM bus pipes are used. OK, so for I/O ports, I just wanted to include these function definitions here so you can see there's really not a lot of magic happening. Any virtual device that wants to receive I/O port notifications needs to implement these two functions, notify I/O port read, notify I/O port write. Just tells you the I/O port address, the size of the access, and a pointer to the data that is going to be read, or it gives you the data that is being written to the I/O port, and you can choose to emulate it however you'd like. And it's really similar for the MMIO emulation as well. You have two functions, notify MMIO read, notify MMIO write. Those functions get called whenever a particular MMIO range is accessed, and the emulator can then go and do its thing. So hopefully at this point you have a little bit of an idea as to how Hyper-V is set up and how you can talk to some of these components. And I'm going to hand it over to Nico, and he's going to walk you guys through some of the cool vulnerabilities that both Microsoft engineers and external folks have found in Hyper-V, kind of get you inspired on what kind of bugs you might find.
Yeah, thanks, Joe. That was really useful. I think it was useful for you. Yeah, when we initially thought about giving this talk, we didn't want to give something just theoretical. We wanted also to show you some bugs so you could understand how things work better, where you could set your breakpoint. So I'll come back to that in a second. So also, another point is that before we ever decided to do that talk, we talked to people who were really curious about researchers, why we had that bounty, but people were not reporting bugs to us. So we thought, oh, what's going on? Is it something wrong, or is it just too difficult? And we had some comments like saying, yeah, Nico, you've got access to all these bugs. You've got the source code. You've got everything. We don't even have the symbols. So the good news is that 6 months ago, Microsoft decided to publish around 40 symbols for Hyper-V. So you don't have the entire set there. For example, Joe mentioned store VSP. It's not available yet. So
well, actually, Nico, I'm going to interrupt you there for a second. Store VSP, all of the storage binaries now for Hyper-V, as of, I think about a week ago, we actually have published all of the symbols for those.
You're amazing, Joe.
They're all there. The only one we're missing is the hypervisor now.
Maybe one day.
Maybe one day, yep.
So yeah, so just keep going to that website, update it, and maybe one day you'll see the missing one. But there is already enough for you to start hunting bugs. So we selected there's 5 issues. Why there's 5 issues in particular? Well, some of them have been reported by externals, and so we wanted to show you how they found them. So you could repeat it. Also, well, all these issues affect components where the symbols are available. So you can actually debug that and put your breakpoint. And crucially, these issues are easy to understand because we've seen some very, very complicated issues. We just don't want to talk about them. So just to come back to Joe's slides, this is what are the affected components here. So mostly in the kernel, VM switch and VPCI, and also some components in the virtual devices. So I start with something affecting VM switch. So what's VM switch? It's a huge component, but basically it's just what provides network connectivity to the VM. So the first bug I'm going to talk about was actually found by somebody from TenSec, Peter Lavati. So he's hiding there. So Peter is a great guy. Talk to him. He's brilliant. He's got very good ideas. So this bug, it was, sadly for us, it was just a story about sending a packet with a long string to the host. And so you've got a function in VM switch that is accepting a packet, and inside that function there is some error checking, and if something goes wrong, then the code just logs that error with that string. So what happens is that if you're running a VM switch with the special pools and you're sending that long string, then you'll end up getting an AV while you're trying to print that string. So it's really terrible. So for an issue like that, right now you would get 15K because this is just a DOS for kernel. So the question you might have is how Peter found that one. He used the Linux drivers, and he just fuzzed it. He took some time to understand how the code worked. He put his fuzzer there, and at some point, I believe very quickly, he managed to get that issue. And since it's really easy to figure out the root cause, he just sent us a POC that consisted in just a patch of the Linux kernel, and then he just asked us to type if config, and that would just send a malicious packet to the host. So that was a very easy to reproduce issue, and we are very happy that Peter sent it to us. One thing, it was just present in RS1. So when you do your bug research, always take the very latest version, because this is where the new features are. And if you're using something from the past, you might just miss it. So yeah, be careful with this. Also, a quick slide just to let you know how things work. I'm going to spend much time on this, but basically, if you want to reproduce that issue, just put some breakpoints on these functions, and you'll quickly understand how things work. Also, to keep last word on VM switch, so we've seen other issues from externals, like Kostya Korchinski from Google. He reported this 2 years ago, I think. Go check out these links. There is a proof of concept. As the issues are detailed. And also check out Jordan Rabbet's talk at Black Hat this year. So Jordan Rabbet is a Microsoft engineer, and he wrote an exploit using several VM switch bugs. And he talked about that at Black Hat. It's really worth it. It's really interesting. So have a look at it. So next bot I'm going to talk about is something that affects VPCI. So what's VPCI? Well, it's basically the component that is used by the guest to use some PCI components in the kernel. So bear something in mind, you need to have some hardware connected to use that component, like for example, a graphic card. So this bug in question, it was found by a team at Microsoft, the virtualization security team. So how they found it? So you've got this function, in a VPCL, channel process packet, which is like a big switch which receives packets from the guest. And there was that threat interrupt packet that was sent by the guest. And so if you look at the code there, you can see that the function is taking some parameters, is sending it to this function here, threat single interrupt. And what's not there is that this function is supposed to return a status code. Okay, and so if everything is okay, then it will also initialize a stack buffer provided by the parent function. But if something goes wrong, that status will actually return the error code. And the thing that we didn't notice is that in such case, it won't initialize that translated message. So you would end up disclosing 10 bytes from kernel memory, from the stack. So a bug like that, right now we would pay $15,000 for it, $25,000, sorry. Yeah. So yeah, it's not that difficult to find. For example, to talk to this component, you can just put a breakpoint on a function named FDO protocol communication. This is where the handshake happens, and it's really easy. This function is synchronous, so you just send your message and you get the response back, and it's really easy to trigger that bug and to see the result, like in this case, disclosing stack memory. So have a look at that. Now we are going from the kernel to the worker process. We are going to talk about some synthetic device, and more specifically, the video synthetic device. So I found that bug a while ago. This bug actually a while ago. So this component is this component is about handling the different resolutions to the screen. So that's what it's doing. So check VMUE devices. There is also other components in that library, and all of them, not all of them, but most of them work with a function called onCreateMessage. So the code is very easy to read. You don't need the source code. You can just look at it in IDA. That's how I found that bug, actually. And yeah, you'll see that it's actually a switch case showing an internal state machine. And for that bug, the idea was the guest would send a message with a Boolean, and if that Boolean was set to false, you would enter a code path where you would allocate 8F bytes of heap memory, but just writing a few of those bytes. So in the end, that message, that block would be sent back to the guest, and you would disclose around 80 bytes of heap memory from the worker process to the guest. So a bug like that right now, you would get $15,000. And the thing with this bug is that when I found it, I also noticed that there was almost something similar, leaking some stack memory. So do something similar, and you'll get twice the bounty. So yeah, it's really worth it, in my opinion.
Yeah, I agree.
Yeah, so again, to trigger that bug, it's quite easy. There is a driver called Hyper-V. So most of that code is used when the VM initializes. So just put your breakpoint in the initialization function, and you'll see how packets are sent. It's really easy to trigger that bug. One thing I didn't mention is that you don't necessarily need to send us a driver or something crazy to show a bug. You could just use a Windybug script and that quickly change the memory and just show us the behavior. Yeah, we really need to. We are really interested by how to reproduce the issue, but for bugs like this, it's really easy to figure out what's going on. So yeah, you don't need something crazy.
Yeah, as long as it's clear to us that the modifications you're doing with the debugger are things that are totally under guest control, then it's totally fine with us.
Yeah, so yeah, be simple. Sometimes, yeah, you just don't need to do complicated stuff. Joe, do you want to talk about that one?
Yeah.
Because you found it.
Yeah, I'll talk about this one. So this was a bug in MMIO emulation. So when the notify MMIO read function gets called in all of the various virtual devices, you will get passed a pointer to this buffer that stores the data that you're basically emulating the read for. So if the guest tried to read 8 bytes, you are expected to put 8 bytes in that buffer. And one of the things that we noticed was that there were a number of functions that would do checks like this one down here you can see in the battery emulator. If the number of bytes that the guest is trying to read is not 4, then just immediately return. Well, the issue there is that you've not actually populated that read buffer at all. And there's nothing here to indicate failure, right? And so what's going to happen when this function returns is some of the Hyper-V code that called this function is going to go ahead and return however many bytes the guest requested from that read buffer. So if the guest did an 8-byte MMIO read, 8 bytes from that read buffer will be returned. And that's uninitialized memory. And in this case, it was actually kind of nifty because it turned out that if you did an 8-byte read, it would reliably leak a pointer to a very specific object that's allocated on the heap. And so it could be pretty useful for bypassing ASLR. And yeah, if you find a bug like this and send it to us, that's $15,000 that you can get in the Hyper-V bug bounty right now. So yeah, it's a pretty good deal, I think.
I'm very glad you caught that one, because I missed it. So the last one we're going to talk about is actually our favorite. It was a bug in the emulated storage. So this bug was reported to us by a finder who wishes to remain anonymous. So basically, what is this? So you've got this storage component that, like the hard drives, CD-ROMs, and floppy are using. And so if I'm not wrong, you can talk to this component using the port 1F0 to 1F7. So the first ports are just to manage the internal state of the machine, but the last one is where you write data to a buffer. And this buffer is supposed to be correctly managed, but there was a case where you could set the state of a machine to an unexpected state. And in the end, you could control the offset where you would be writing to that buffer. So what happens is that in the end, you would be able to read-write data on a 4 gigs area. So that's exactly what you need to build to write an exploit. And we're quite happy right now because this is the bug that got the most bounty so far, $150,000. Yeah, so we are really looking forward for this kind of research. So please find something like that, and you'll get a huge paycheck.
Yep, and that's not a theoretical bounty, right? We paid this to the person.
We paid this.
Yeah, we paid $150,000.
Yeah. So Joe, do you want to wrap this up?
Yeah. So you know, I'm really hopeful that this talk was useful for you guys. I'm hopeful that some of you guys are interested in working on Hyper-V. And we really want to pay bounties for Hyper-V. We have money set aside for it. We want the bugs. So let us know if you have any questions. Let us know if you need any other tips. Please check out the appendix at the end of this slide deck. We have really packed a lot of information into the appendix that will be useful for you guys if you want to go and find entry points and find other useful information about how to start finding bugs in Hyper-V. And yeah, we're looking forward to working together with you guys and hopefully paying out our first $250,000 Hyper-V bounty.
Definitely quick for that.
Yeah, thank you.
Thank you.